In this section, we're going to talk about a special kind of a linear transformation. It's called a reflection. And I think you've already seen reflections. You may not remember, but if you go back to pre-calculus, algebra, let's take a look at what you should already have seen this. Let's take a function from the reals into the reals. And we would say that that function is symmetric about the y-axis. So it's a mirror image on the left and right of the y-axis if f of x is equal to f of negative x. So for example, and that has to be true for all x's. So for example, if x is 10, the height or value of the function at 10, which would be f of 10, is the same as the height at f of negative 10. Okay, so that gives us a mirror image about the y-axis. This means that the graph of f remains unchanged after rotating it about the y-axis. So you flip it around. I mean, one simple example is f of x equals x squared, which is that parabola. Well, you notice it's the y-axis here is the mirror image on the left and right. If you rotated it around the y-axis, you would get the same graph. Okay, and in this case, we happen to say that f is called an even function. Examples of even functions are, well, I'm going to use any polynomial. I'm going to get this one out of the way, the f of x equals x squared. Any polynomial that has only even exponents for the x's, like say g of x equals 3x to the fourth, that's even, plus 2x squared plus 9, something like that. All of the x's have even exponents. So that's just two examples of even functions. The other type of symmetry is not around a line, but around a point. So let's say f is symmetric about the origin, that point, 0, 0, if f of x is equal to, well, very similar to what we had up here. Instead of being equal, f of x equals f of negative x, you put a negative sign out in front of that. And technically, if you wanted to, you could have put the negative sign over here. Negative f of x equals f of negative x. And multiply both sides by -1, and you would get exactly what I have here. F of x is equal to the opposite, or negative of f of negative x. This means that the graph remains unchanged after rotating it 180 degrees about the origin. In this case, we would say that f is an odd function. Examples of odd functions are, well, I'm just going to write down some simple examples. F of x equals x cubed. Any polynomial function, g of x equals, say, 4x to the fifth plus 2x to the third plus x. All of the exponents of the x's are odd. Notice that we don't write it, but x is x to the 1. So this is simply two examples of odd functions. And let's take a look at, just to remind us, what f of x equals x cubed looks something like this. You can see that if you rotated it around this either clockwise or counterclockwise, doesn't matter, 180 degrees, you're going to get exactly the same graph. Okay, so hopefully that rang a bell from back in your pre-calculus days. Now let's look at how we're going to define these in geometry. Number 2 here. Definition. Let F be a transformation on a plane, calling the plane P. It could be the XY plane. And let script L here be some line in the plane. Okay, so I'll use this example later, but this piece of paper, if you extended it, would be the plane P. Here's the definition. F is a reflection on the line L if, or if and only if, the line L is the perpendicular bisector of what? Perpendicular bisector of the segment A prime for every A in the plane P. Now remember what we call A prime. We've been kind of defaulting A prime is F of A. So F would be the reflection if that's true. And we'll do an example here to show exactly what we mean. Now we denote a reflection. We usually use, instead of an F, we use a little s instead of a little f for the function. And then subscript L is the line that it's reflecting around. So it could be the x-axis or the y-axis, but it certainly doesn't have to be. So let's show exactly an example, a simple example of a reflection about the line M. M is right here, this line right here. And notice that I have a triangle on one side of the line, and the vertex points, the vertices are A, B, and C. Let's draw the reflection of that, what we would call little s M. Okay, here's exactly how we would get it. Let's start with the point that's closest to the line L. Let's start with C. Drop a perpendicular from C to the line M. I may have referred to it as L, but this line is M. And do the same from A. Drop a perpendicular to the line M. And do the same for B. I'm not using a straight edge, so I'm just kind of guessing here. Well, here's what we need to do. We need M to be the perpendicular bisector of the line A prime, B prime, and C prime. So we need to extend this. Let's start with C and make it just exactly as long, as double the length, from C to the line, and then go out that much farther to get to C prime. So now you can see that the line M is the perpendicular bisector of the line segment C prime. Now let's do the same thing with A and B. So extend these line segments exactly the same length. That'll be B prime. And then A prime be about like maybe that. Is that about right? This length should be the same as this length. We'll call that A prime. And you could do that same thing with all of the other points on each of these line segments, the sides of the triangles. But you don't have to do that. All we need to do is connect the line from A to C. Well, connect the line on this side from A prime to C prime. And then from B to C, which would be like B prime to C prime. And then from A to B, we need to connect A prime to B prime. Okay, so that's not perfect. My drawing wasn't perfect, but if I had done it perfectly, this triangle, maybe I'll shade it in a little bit. The triangle and its interior would map to this triangle and its interior. So you can see that the line M is kind of the reflection, kind of the mirror when you put it this way. The left half, if you folded it over on that line M, this would match this perfectly. Okay, so a simple example of a reflection around a given line M.